this morning in this room. The first talk is given by Professor Chi-Wang Shu. I think everybody in the numerical analysis and the scientific computing will have heard this name. He is a big figure and a huge mountain in this area. He is a SAM fellow and ICM speaker and AMS fellow. Okay, today he will talk about discontinuous Galerkin method, please.
Convection yeah, good. Much louder. Convection dominated convection diffusion equations and the convection dominated convection dispersion and other higher order PDEs. So with that, then I will give some conclusions. So the original discontinuous Galerkin method designed very, very early in the 1970s. They were used to solve hyperbolic problems, in particular time-independent steady-state linear hyperbolic equations, so-called neutron transport equations. And they are very successful. When they were introduced immediately, they were picked up by numerical analysts to study the properties, stability, accuracy, and so on, and they were used quite extensively. However, this talk will concentrate on time-dependent PDEs. That would be the PDEs of this form. I don't think this thing would work. So of this form, u sub t is the partial derivative with respect to t. So with time there, we are going to treat only the spatial derivatives by discontinuous Galerkin method. So this fu sub x, or in the 2D case, fu sub x plus gu sub y. So hyperbolic equations means that you have some, so this I will just mention briefly, some PDE level. The solutions may become discontinuous, and weak solutions must be defined, but they are not unique. So you would have to pick out of many, many weak solutions, one of them, which is physical, which satisfies the so-called entropy inequality. So these are all mathematical backgrounds for such PDEs, for hyperbolic PDEs. Now, we are talking about numerical methods. So how do you do that? Well, there are many different ways. One possible way is to mimic what people were doing for defining weak solutions, right? So what you do is you multiply it by a test function called v here, and then you integrate, and you integrate by parts to throw the derivatives on u to the test function v, Here, since I'm going to apply discontinuous Galerkin only in the spatial variables, I'm not going to do the integration by parts here, because my test function v does not really depend on t. So I'm trying to do only spatial discretizations. Of course, if you do space-time discontinuous Galerkin method, you would have to also to integrate by parts here in t. Here, I integrate by parts only in x, so the derivative will go to the test function. But of course, you also pick up two boundary terms, right? Integration by parts formula from high school. So these two terms on the boundary in 1D these are just point values. So I pick an interval ij. So on the two boundaries of this interval, I will pick up these boundary terms. So this, of course, is just equality, right? So if you have an exact solution of one of the PDE, if we are given any test function v which is differentiable, then this is an equality. It holds for every test function v. So I would want to invert this equality into a scheme, computational scheme. So what you do is that you now abuse notation. Well, you shouldn't abuse notation. You should probably denote the numerical solution by u sub h. But here, let me just be lazy. So I abuse notation. I still use the letter u, but test function v. But this time, I assume my u is no longer the exact solution of the PDE, but the numerical solution, my numerical approximation coming from a finite dimensional function space, what I called VH. Now, usually for discontinuous Galerkin people, this VH consists of piecewise polynomials of degree k, which means you have partition in 1D. You have a partition of the interval from 0 to 1 into pieces, n pieces. In each piece, in each small interval, you have a polynomial of degree up to k. But between two cells at the interface, you allow your approximation function to be discontinuous. So that is why this is called the discontinuous Galerkin method. Clearly, this is a finite dimensional space. The dimension is actually, in this 1D case, it's just n times k plus 1, right? Because in each interval, you have k plus 1 degree of freedom, and you have n intervals. Finite dimensional, then I would want to find u in this space, such that for every v also in this space, I will have some, I will have this equality. This equality, I'm hoping that I will have this equality holding, I want to find a u in that finite dimensional function space, such that for every v also in that finite dimensional function, the same space, this equality holds. But if you look at this equality, there's no problem here integral, there's no problem here integral, right? But there are problems in these boundary terms, because you told me that the function space could allow discontinuities at ij plus half. So if that is the case, this notation uj plus half doesn't make sense, because at j plus half, I have a function which is discontinuous. I have a left limit, I have a right limit. They don't agree. So you have to tell me, what do you mean by uj plus half? Same thing. You have to tell me, what do you mean by vj plus half? Because v comes from the very same function space. It's discontinuous. So how do you treat these terms? So that's the only sort of freedom you have in designing DG, right? And that's what you explore. So this is what you do. For this ambiguous f of uj plus half, you replace it by a function of two variables rather than one. So put a hat there, put two variables. And you told me there are two values, left limit, right limit. So I use both of them. So if I use both of them, I have the so-called numerical flux, which is a function of two guys. But of course, it cannot be an arbitrary f hat. So it has to satisfy several properties. The first property is consistency. So what happens if the function happens to be continuous there? Then you better recover the physical fu. So that's the first part. The second part, which is crucial for stability, is the so-called monotonicity, which is upwinding, which means that this function has to be an increasing function in the first argument, decreasing function in the second argument, in the general sense. So increasing means non-decreasing. Okay, and this is what you do with this ambiguity. Now, this ambiguity on V is simpler. So you just take it from inside ij. So if you are integrating in ij, on the right boundary, you take the left limit. On the left boundary, you take the right limit. So take it within the cell for the test function. So these two things are treated differently, notice that. So after that, that's the scheme. I have taken care of this ambiguous boundary terms, and everything else I leave the same. So that's my scheme. So certainly you would ask, oh, okay, would there be a unique U satisfying this equality for every V? Yes. So you can actually write them out, write the solution out, and you can go to the computer and implement and so on. So the scheme is pretty simple. And since you are just using integration by parts, 1D and multi-D, they are the same. So in multi-D triangles, you just use integration by parts, which is called divergence theorem, or Green's formula, or whatever. So it's exactly the same. that's one advantage actually of finite element methods, that once you figure out how to do it in 1D, basically you are done in multi-D unstructured mesh. Okay, how about the time? Now, I told you that I'm discretizing only the spatial variable, so time I'm just using the usual so-called TVD Runge-Kutta, which in the third order case is just this. So you have different orders of accuracy of different formulas, but in a sense, I'm not really using DG in time. In time, I'm using the usual ODE solvers. Okay, so so this is the scheme basically. So what do you get out of this scheme? There are actually several advantages, properties and advantages that I would want to summarize. First of all, this is a finite element method, so it can treat general geometry very easily. So just like I mentioned, I put down the formula in 1D, but in 2D, 3D, 2D triangles, 3D tetrahedrons, it will be the same. Also, it will allow hanging nodes. So this is sort of unique. Well, not unique, but it's easy to do in DG. So hanging nodes means that if I have a triangle in 2D, right? So this is my mesh. I decided that I want to refine here, but not here. So I just put it this way. Now, this is called a hanging node because it stops here, it doesn't continue. For general finite element methods, continuous finite element methods, this could be a problem. Could be a problem because you want this to be continuous. You want the function to be a polynomial here, two different polynomials here, but it has to be continuous along this side. That's, you can imagine that could cause you some problem, right? Why should two different polynomials here agree with a single polynomial on this side? Right? But for DG, of course, doesn't matter because I told you that I'm allow discontinuities. So hanging nodes is fine. It's very compact. You can see that when I'm evolving the solution in cell I, I'm talking only to my neighbors through this numerical flux, through this f hat that I mentioned, right? So I talk only to my immediate neighbors. So for example, in 2D, in order to evolve the polynomial here, I will talk to this guy, this guy, this guy, and this guy, right? So these are my three neighbors. That's all. I don't talk to neighbors. So this is a big advantage in data management and also parallel computing. It's an explicit method I use Runge-Kutta. And hence, because of this, it's very friendly to parallel machines. So parallel efficiency is very high for DG methods. Now, theoretically, this very simple-minded method has a beautiful mathematical properties. For example, I mentioned that this weak solution is not unique unit entropy condition. That's on the theoretical side. However, how about the numerical scheme? You can prove very easily that your numerical scheme, the solution, this U is my numerical solution, it also satisfies the so-called cell entropy inequality, which is the counterpart of the PDEs entropy condition. Of course, only for this entropy. Yeah, so this is very nice, right? So basically, it implies immediately the L2 stability. So this is true also for any dimension, space dimension, any order of accuracy. It's very amazing that you can use very, very high order DG. You still have this property in multi-dimensions, triangles, everything. How about the systems? Well, for systems, for a long time, we could do it only for symmetric systems. That is f prime of U, which the Jacobian is a symmetric matrix. Of course, there are some systems which are symmetric, but not all, like say Euler equations of gas dynamics is not symmetric, only symmetrizable. So for symmetrizable systems for a long time, we wouldn't be able to get this cell entropy inequality, but that's overcome also in more recent years. So you could actually, so it starts with this paper of Chen, my former student. Yeah, and then picked up. So basically, you could say this method has very good theoretical properties. And it's very accurate. So error estimates occupy a big chunk of study on DG methods. So you want to say, okay, I use polynomial of degree 5. I want a 6th order method. right? Degree k, I want k plus 1 for that of accuracy. So often this is true, but you have to prove it. But occasionally you can only get k plus half, and sometimes it is even sharp. So these are technicalities, right? So if you go to this route, you will be able to do a lot of theoretical numerical analysis work. But in summary, basically, you get what you expect. You use the method, it will be stable, it will converge most oftenly in optimal order of accuracy. And you can even get super convergence. So that's the proof is probably a bit more difficult, but you do get it. So you use polynomial of degree k in certain norm, weak norm, and so on. You get actually 2k plus 1, which is this is double, right? So you get k plus 1 for strong norms, but you get 2k plus 1 in certain cases, either weaker norms or in a certain special case, and so on. Superconvergence. How about, so all the previous case we're talking about now, let me put it this way. The stability part, cell entropy inequality, and so on, these are for any initial condition, any initial condition, discontinuous or not, any solution. However, for the error estimates, the one I mentioned before were mostly for smooth solutions. So solutions which have many, many derivatives, continuous derivatives. But I mentioned at the beginning that hyperbolic equations unfortunately could have discontinuities. So this assumption may not be valid. So what happens if your solution itself is discontinuous? Then the error estimate is a bit more involved. So you would have to estimate maybe a certain distance away from the discontinuity. Then you would be able to get error estimates. If you include the discontinuity, you may be able to get error estimates in weaker norms, for example, negative Sobolev norms. Then you could also get high order accuracy error estimates. But if you want the strong norms, you can look at the solution. You might be convinced that in strong norms, high order accuracy is not possible, right? So this is your theoretical solution, discontinuity. This is your numerical solution. One transition point, transition cell. It's inevitable, right? So, but this guy screws up everything because if you measure it in L infinity norm, the distance is order 1. So in L infinity norm, you don't have convergence, right? Because this guy will always be there no matter how you refine your mesh. If you use, of course, L2 norm or L1 norm, then certainly this order 1 quantity is multiplied by the cell size, so that's better. So you would be able to converge, but at most first order, right? Because this order 1 guy times delta x is already first order. So you cannot really get anything higher than first order if you measure it this way. But that's the wrong way to look at it. You should look at it in the negative norm, but weaker norm, integral norm. That way you would be able to get high order accuracy, even for discontinuous solutions. Okay. And then these are more recent things, so they are, certainly you would say, well, it's done. DG method is done. Why are you still working on it? Well, if you actually use it, you find out there are many, many unresolved problems, right? You only look at the good things. But for example, you run DG method on the Euler equation or Navier-Stokes equation, your code, you put it into the code, you go to lunch or dinner, you come back, the code crashed. So you are very upset, right? So why does it crash? Because it computes negative density, negative pressure, and then brings you outside of the happy hyperbolic regime. You know, the Euler equation of gas dynamics, if you have a negative density or negative pressure, then the system becomes non-hyperbolic, becomes mixed type, and then that is ill-posed. Then it just blows up. So you would need to spend the time on designing DG methods which are bound preserving. Namely, it will not happen that you can get numerically negative density or pressure. Then you can safely go to lunch or even go to sleep, and next morning the result will be out. Actually, it's the same. It's a true story, right? I have a collaborator, Long Long Feng, in astrophysics. So basically, he told me that he's computing, and then this code, big, huge code, right, to compute, and then you have to sit there because once it crashes, you save the previous time step or maybe previous 10 time step solution over there. You restart from that thing. You reduce the time step. You continue. You hope that it will go through. So you have to sit there do this computation. So with myself, he will be able to go to sleep. Right? Code is safe. Put it there, run overnight. So tomorrow you get results. So that's very nice. So these are things that you always pick up issues that you can work on, important issues. So I guess this is the continuation of this bound preserving. A lot of work in bound preserving. Right? I just mentioned them briefly. Limiters, which means if you have very, very strong shocks, then the solution still will be oscillatory. So how do you deal with these things? A lot of studies on limiters. Singularities. So now, of course, discontinuity, this thing is also a singularity. But what happens if your exact solution is the derivative of this guy? If it is the derivative of this guy, it's a data function, right? Very difficult to compute. Right? Especially for finite difference method to compute the data function. Usually people smear it over several cells and then try to compute. But for DG methods, you don't have to smear it. So that's the beauty of integral-based methods, right? You can actually compute using DG methods together with the bound preserving technique. You can beautifully compute, for example, pressureless Euler equations that allow data singularities. So in many other situations, physically, the PDE allows data function type exact solutions. Then you can use these methods to solve. Arbitrary point clouds. This I like. So I mentioned the discontinuity. You use limiters. A lot of people came back to me. So yeah, you are essentially a finite difference guy or finite volume guy. You put limiters there. Finite element people do not like limiters at all. So they want everything to build into the variational formulation. They don't want that you compute the solution for a one-time step. You feed it into another post-processor limiter, and then, right? Because it's not very beautiful. For one thing, it is very hard to analyze theoretically for another thing. So very nonlinear procedure. So for example, what happens if you use limiters? Do you still get high order accuracy and other things, right? It's very difficult to analyze. So this is for two of my former students, Lu and Liu. So this is South University of something in Guangdong. This is Academic Sinica Computational Math Institute. So there's this oscillation-free DG, which means you put something inside the variational formulation. You control oscillations. At the same time, you prove everything that you proved for the original DG. Stability, cell entropy inequality, error estimates, entropy condition, whatever you want. So then you will have effective control on oscillations. Of course, the referee complained that oscillation free, but it's small oscillations. You see, shouldn't call it oscillation free. Okay, essentially oscillation free. Essentially oscillation free is the title of one of those papers. But if the referee doesn't complain, then we still call it oscillation free. Okay, HP adaptivity, which means HP adaptivity means this. Basically, this is H adaptivity I refine, right? I don't like this, I refine. P adaptivity means that I put polynomial degree 6 here, 7, 3 here, 3 here, for example, and 7 here. Of course, there must be a reason for you to do this. What I'm trying to say is that DG framework would allow you to do this kind of choice of polynomial degrees. Whether you do need to use that or not depends on the so-called error indicator. So there should be mathematics guiding you to say what would be more economical. Should I refine or should I increase polynomial degree here if I view the error to be too big? And there will be mathematical guidance to tell you, okay, in this situation, it is better to refine. more economical to refine. And in this situation, it is more economical to increase polynomial degree. So once other people or you yourself, the other part of you, decided using mathematics error indicators to tell you that you should use polynomial 6 here, 3 here, 3 here, 7 here, the DG method allows you to do that with no modification. This is not true for many other methods. For example, if you have a continuous finite element, you may not be able to do this because a 6-degree polynomial, a 3-degree polynomial, a 3-degree polynomial, how do they agree here? Right? How? Because continuity means they have to be the same polynomial along this line. That's a very tough requirement. But for DG, of course, I don't care. I allow discontinuity here, allow discontinuity here, so you can immediately, the same framework, allow that. So these are all advantages that explains why people would like to use DG. And then the last part is what I want to explore in the later part of this talk. Stable and convergent DG methods are now available for many other PDEs. So at the beginning, we were almost exclusively looking at hyperbolic PDEs, which is nice, right? A lot of good properties and very useful. But people would come back to say, my equation, my PDE is not really hyperbolic. It has a small right-hand side which has second derivative, right? Some diffusion. So what do you do? Of course, at the beginning, we told them, okay, you use DG to treat the hyperbolic part, and you use your old mixed finite elements or whatever method to treat the second derivative part. You could do that, and we have papers on these things, but the coding is a bit messy, the analysis is a bit messy, right? If you combine two methods, it's a little bit messy. So it will be much better if you can unify the algorithm under the DG umbrella for all terms. So that would be the remaining part of my talk. But before that, the history of DG, very incomplete. I mentioned to you the 1970s, right? So all this business started in the technical report, Los Alamos technical report in 1973. That is the first DG method for steady-state linear scalar conservation of the so-called neutron transport. And then immediately, 1 year after that, the French mathematicians, numerical analysts, Lassant and Raviat, so they proved stability and error estimates for this method. And then the error estimates are improved in a sequence of papers by Clay. This is Clay Johnson in Sweden. And then comes to Cockburn and myself. Bernardo Cockburn was actually also here last week. I don't know how many of you went to his talk. Yeah, so he also gave a talk. He got a prize for one of the DG papers. So he gave a talk last week here on DG also, on DG, on the so-called HDG, so hybridized discontinuous Galerkin method. So both of us were actually postdocs at University of Minnesota in 1976 to 86 to 87. That was the IMA Institute for Mathematics and its Applications. That year was the year of scientific computing. So we were both there as postdocs. And then we started talking and working on this thing. Happily, a lot of results came out of it. I mentioned this cell entropy inequality. And many things, proceedings, books, special issue, journal special issues, books, book chapters. Let's see, books. Okay, I forgot to list. That's actually a very recent special issue on DG methods in the journal CAMC. So communications on applied and computational mathematics. Yeah, so there's a very recent special issue on DG also. I should list here. Okay, now let's show you some numerical examples of hyperbolic. Right, so this is hyperbolic. Discontinuous, this is P1, and this is P6. The the squares are the numerical solution, the cell average, basically, one value per cell. You can see that you increase polynomial degree becomes much better, right? Resolve this discontinuity much better. Of course, you have over and undershoots because I have not used any of the limiters and so on. But still, even without using the limiters, you can see I can tolerate this kind of small overshoot, right? Because it's really very sharp. The discontinuity is resolved very nicely. So 2D also the same thing, P1, P6. And you can also see that this is again a scalar variable coefficient scalar equation. And the solution looks like, so this is the zero level set of the solution. What you are seeing is actually so there's a red part, which is the DG solution, P4, computed on the 24 by 24 mesh size. Very coarse, it's not very refined. And then the solid lines, black line is the exact solution. You don't even see the red lines, which means they are really overlaying on each other very well. Even when they are the exact solution, numerical solution, they agree very well. And then they unwind. Finally, they become this. Then here you can see a little bit red thin, right? Which is an error, but not too much. So this is actually pretty good performance, considering that it's only 24 by 24 mesh, right? Coarse mesh. So DG is quite amazing in terms of wave resolution property. This is the previous one is linear. This one is nonlinear. You compute this kind of things, and you compute, and they look pretty similar to each other. This is a P2 with 1/240 mesh size. This is P1 with 1/480 mesh size. They are basically comparable. But of course, this is much cheaper than this, much coarser mesh. Even though per cell cost is larger, however, you really have many, much four times smaller, right? It's only 1/4 of the mesh size here. So, and plus the time step is also bigger. So actually you run, this will be much less expensive than this, telling you that you should use higher order methods even for discontinuous solutions. This is the data function I was murmuring. So this is an equation from population dynamics that you can actually have data function solutions, this kind of solutions. So these are a bunch of data functions. This is P1, I think. No, this is P0, this is P1. So you see this is taller. Taller the better, because the data function, what is underneath the area underneath this is the same. So if it's taller, it has to be narrower, right? And it approximates data function better that way. So P1 performs better than P0 in this case. And you can do same thing in 2D, right? This is the data function I mentioned. You can compute in this kind of solution. This is two types of data functions. This is in 2D, you have two types of data functions. One is along a curve, along a one-dimensional thing, and the other is along a zero-dimensional thing, right? So it's a point. So this looks very simple. For this, we know the exact solution, so they are approximating the exact solution quite nicely. This is the data function here. This thing inside is very near vacuum, so you can compute very nicely. So that's a hyperbolic. Okay, very nice. So then people told us that, oh, I want to solve never solved. I want to solve PDEs with higher order derivatives. At the beginning, we were saying, okay, yeah, just use whatever you want for the second derivative, mixed finite elements or whatever. And we have our own papers on that also, solving semiconductor device simulation PDEs using DG on the hyperbolic part and other finite element methods for the diffusion part. But can we also use DG on the diffusion part? So we started, of course, you always start with the simple thing, right? You start with heat equation. So can you do DG on this guy? You would say, why not? Didn't I write down the previous DG for hyperbolic conservation laws already? Wouldn't the heat equation also be a conservation law if I replace Fu by minus Ux? It's Ut plus parenthesis minus Ux sub x equals 0. So if I replace, everywhere I see Fu in my scheme, I replace it by minus Ux. Then formally I can write down a scheme. Just the hyperbolic scheme. Everywhere I see f of u, I replace it by ux. Remember, this was some negative sign, so this becomes positive ux. I put the ux hat here, ux hat here. So everything, I just copied down the scheme with everywhere fu replaced by minus u sub x. But you have to tell me this flux, right? Remember, this is the flux. Before I had this monotone flux, f hat u minus u plus, with property like it's increasing in the first argument, decreasing in the second argument. Right now, it's not even a function of u, it's a function of ux. So I cannot use a monotone flux, there is no such thing. So what should I use? Well, you may argue, why don't I just use central flux? Ux, I have a polynomial at this location, right? At this location, I have ux from the left. It's a polynomial. I can take the derivative from the left, take a derivative from the right. So that's ux minus, that's ux plus. Put this in here. Good, this is a scheme. Go to the computer. 10 minutes later from the hyperbolic code, you find out this code. Go and compute. Build an error table. That doesn't converge. Zeros order. So you look at for bugs, right? So this is what you do. Must be a bug in the code. But the code is so simple. And the code works for hyperbolic problems. So what is happening here? So, and you look at the picture. The solid line is the exact solution. These circles, these squares are the numerical solutions. They look totally different. And also, this is P1, this is P2. They look different in a different way. So the P1 is different by too high. The P2 is different by too low. It doesn't make any sense. So if you look at this, and you refine the mesh, by the way, you are you're a well-trained numerical analyst, right? So you say, okay, if I see this, maybe my grid is not refined enough. Let me refine the mesh. Right? You refine until you have 6,000 points. It's still on this bad guy. Seems to converge to the bad guy. So then you really get confused. So what is this junk? And then you will say, maybe the method is inconsistent. Because you now recall, right? You learn finite difference courses, and you have this Lux theorem telling you that if you write down a finite difference scheme, if it is stable and it is consistent means local truncation error goes to 0, which means you use the scheme for one-time step, the error goes to 0. So if your scheme is stable and consistent, then it must be convergent. This is the last theorem. And this is if and only if. Which means if it is convergent, it has to be stable, it has to be consistent. It has to be stable and has to be consistent in a certain way. And you see this, you might say, okay, this might be, looks like it's stable because I can compute for 6,000 points. It has to be stable. And it doesn't converge, or it converges to the wrong thing. Maybe it's inconsistent. Then we were analyzing this, right, with my collaborator Mengping Zhang at USTC. We were analyzing this thing, and we find to our surprise that this method is actually consistent. Actually, the good method is not consistent, but that's a different story. But this method is consistent. So then I said to Mengping, either you made a mistake or Lux is wrong, or the method is unstable. Because, right, Lux says if the scheme is consistent and it's stable, it has to be convergent. I'm seeing that it's not convergent, and you are telling me it is consistent. So you have to prove it's unstable. It is unstable, but it's very difficult to prove this thing is unstable because it's a very, very mild instability. It's not like exponential blow up, right? Like I mentioned before, the code just crashes. This code doesn't crash. Even if you put 6,000 points, they compute nicely because it's a very, very mild instability, but you can analyze. Yeah, you will finally find out that this scheme is mildly unstable. So Peter Lux is still correct. It's always correct, right? So stability plus consistency imply convergence. So this is a bad scheme. To tell the truth, so this scheme has been used to solve Navier-Stokes equations and has published the papers. This is because this kind of things, if you only put color pictures, you won't see anything, right? In color pictures, they will be very beautiful. So if you don't do your groundwork, start with very simple scalar equation and table the errors and then find out the problem. If you directly jump to two-dimensional Navier-Stokes equations and use this method, compute and take a graphic output, they do look very nice. So you can publish papers in AIAA journal. Yeah. Anyway, so be careful. Okay. Yeah. So I mean, it's proved in this paper that this is consistent but very weakly unstable. This Zhang is Mongping Zhang from USTC. Okay. Then what do you do? Then it comes to the LDG scheme. So again, I was saying that you have this bad paper published in AIAA journal, so you complain that okay, engineers they're not careful. I shouldn't say that because this thing, this LDG also starts with engineer, right? So these two people are engineers, Bassi and Riemann from Italy. So they have this scheme that works very nicely. And Quattaroni, who was Quattaroni is a mathematician, so he was in that same university. So he was in Minnesota for 1 year. Minnesota was trying to recruit him. So he was in Minnesota, and then he knew Bernardo Cockburn, who is also at Minnesota, faculty member there. Then so he told yeah. So basically, this is the story. Bassi and Riemann were engineers, so I was asking Quattaroni what would be a good method to solve. I have this Navier-Stokes and so on. So Quattaroni says, well, it seems that there's something called discontinuous Galerkin method by this Bernardo Cockburn and Chi-Wang Shu. Maybe you can take a look at that and compute. And then they went ahead. They didn't ask us. They read our papers on Euler equations, and they say, okay, Navier-Stokes, they are second derivatives, so they feel it's very natural to treat the second derivative the way I will explain what they did. And then they compute, get very good results. And then Quattaroni came back to us. So Bernardo Cockburn and myself, we were saying, Bernardo is a well-trained finite element person. He told me, oh, this looks like a mixed method, so you have to be very careful. So usually mixed methods. Mixed methods means that you rewrite the second order PDE to a first order system. You do this quite often in ODE, right? So when you teach first year ODE, you have U double prime plus Y double prime plus A times Y single prime plus BY equals F. You define Y prime to be Z, and you rewrite this ODE, second order ODE into a first order system, right? You do this very often. So you teach students to do it this way. So this is essentially what they're doing. You call UX to be something called Q, and then UT minus QX. So formally, you don't see second derivative anymore. There's only first derivative. Then you use the hyperbolic step to approximate this. So this is typical mixed finite element method approach. You should have something, so this Q and U should come from different space and so on. So there's a matching. Stability relies on a lot of different things. So Bernardo was telling me it shouldn't work, but it worked, right? So we were ashamed that numerical analyst, the engineers already made it work, and we were not able to say anything. So we should say something. So then we looked at their thing, and we made some small changes in the fluxes, but even their choice of fluxes are fine. And this is the DG of the hyperbolic thing. These are the numerical fluxes. Local means that this Q can be solved from this second equation locally. So if you are in this cell, the Q in this cell depends on U in this neighbor's plus cell. That's all. So if you know U in these 4 cells, you can compute Q. So that's why it's called a local discontinuous Galerkin. So Q is actually not a new variable. It's a represent. You can obtain Q from U locally. You don't need to solve a big system. So this method, the numerical flux, it turns out that the best choice of numerical fluxes are these alternating ones. So you take one from the left and the other from the right. It doesn't matter which one you take from left, from right, as long as they are alternating. And also you can choose central here. So central is also fine. But central, you lose a little bit of accuracy. And then the method becomes stable. And surprisingly, the proof is trivial. We were looking at this. So at the beginning, we were saying this shouldn't work. And then when we wrote it out, that, oh, it's trivial. And then Bernardo says, it's trivial. So we couldn't write any papers, such a trivial thing. Still write, why not? So we still wrote a paper on LDG. And of course, this is one of the most highly cited papers, right? This is the first LDG paper that you can. But you can see that the proof is trivial. So it's just like the hyperbolic proof. Nothing fancy at all. So this is also an advantage of DG. It's much, much easier than the mixed finite element proof, right? And the good news is that it can treat nonlinear things in equal way. So you start from heat equation, but then you treat general nonlinear convection diffusion. You can get it done. And you get error estimates and so on. Okay, good. So this time, the LDG, then you get second order for P1, third order for P2, and so on. You can prove, and also you can superconvergence, Mason principle, nonlinear. So this is the porous media equation. So this is this equation. I have this. No. This equation. So this M, if it is bigger than 1, is nonlinear, right? So this comes from oil, porous media equation. Yeah, works very nicely. So this I will skip. So unlike for hyperbolic equations, for which there is essentially only one DG, if two people have two different versions of DG, they might have chosen different numerical fluxes, or maybe limiters and so on. But essentially, there's only one DG. But for anything higher than first order, let's say heat equation and so on, second derivative, third derivative, there are many, many different versions of DG. So the LDG that I mentioned is only one version, HDG that Bernardo talked about last week, internal penalty DG, ultra-weak DG, so there are many different DG methods. They all have their pros and cons. So of course, for every one of these DG methods, you would have to prove the same thing, right? The stability, error estimate, and so on. But then also, they have different advantages in certain situations. So that's why they can all survive, right? So certain situations, you should use one, and other situations, you should use the other. And time stepping. Okay, so how about the even higher orders? So if you go jumping from first order to second order is a big jump. Second to third, maybe it's a much smaller jump. Yeah. Third order, of course, is this KdV, this water waves, right? So KdV equation. There are 3 derivatives here, and also could be nonlinear. So once you know the trick, you just repeat, right? So this, you introduce 2 auxiliary variables. So Q is Ux, P is Qx, which is Uxx, and then becomes Ut plus Px equals 0. So 3 equations, but each one of them has only first derivative. So then you could use hyperbolic treatment for these first derivatives. You're in very good shape. Write down the scheme. They are all local, meaning that they can all be, the Q here can be obtained by P in these 3 guys, and U here can be obtained by Q in these 3 guys, and so on. So all local. So these auxiliary variables are not really variables because they are essentially just U locally. But you write them this way, the choice would be these numerical fluxes. You have to be careful. How do you choose these numerical fluxes? For that, you spent, so this was, I remember, PhD thesis of Chi-Wang, who is faculty now at the Iowa State University. So when she was doing this, we were saying, okay, so it's the second order equation is diffusion, but the third order PDE is actually also a wave equation, water waves, right? If it's a wave, it has a preferred upwind direction. The upwind direction for this case is from right to left. So you should take this. There are three numerical fluxes to choose. You should take more on the upwind side than on the downwind side. So you take 2 from the upwind side, the plus, and only 1 from the downwind side. Of course, you could also take all 3 from the upwind side. That's also upwind. But it turns out that's an unstable scheme. So it means that you have to be 中庸之道. You have to be upwind biased, but cannot be completely upwind biased. Right? If you have all 3 upwind, this turns out to be a bad choice. But if you have more upwind than downwind, 2 versus 1, that's a good choice. Then you get a stable method. Of course, which 2? And turns out that the middle guy has to be the upwind. So this Q has to be plus. And these 2 guys you can alternate. So either plus here, minus here, or minus here, plus here. So they're both okay. And with this choice, you prove a lot of good properties. First of all, you compute, you get beautiful error k plus 1 order accuracy, and you can prove all these things. So not trivial. The proofs are much more involved. Error estimates are much more involved for KdV type equations than for hyperbolic conservation laws, but you can do that. You can do that. You compute, it looks, this dispersive wave, you get all these oscillations. Notice this is physical oscillation, right? It's not a numerical oscillation. So dispersive waves. One wave becomes many. So you can compute and you get these guys. Very nice. And then you get all these equations. By the same token, you can also do 4, 5, 6, 7, 8. So it turns out that all the even guys have one category, is called diffusive type PDEs. All the odd guys are the dispersive type PDEs, and their treatments are similar. So you can also do the biharmonic and other Kuromoto-Swasinski and the other types of. There are a lot of such PDEs for some reason from mathematical physics. So many. So we are always given these equations, and we ask each time they give us this equation, we'll say, oh, do you have an energy? Usually you do, right? It comes from physics, so there should be some energy, which is under control. So how do you prove in a PDE case? It's very nonlinear. How do you prove this particular energy does not increase with time? How do you, in the PDE level, on the PDE level, how do you prove that? So you sit there, they tell you how to prove this, and say, can I mimic this from my scheme? So that's the research, right? Try to get a scheme which follows that line and still have the same stability in the same energy. Okay, Carr-Hilliard surface diffusion. This is much more technical, so I don't want to talk about this. So I mentioned there are several different types of PDEs for PDEs of higher order, right? Starting from diffusion already, KdV and so on, LDG is no longer the only choice. You would have internal penalty DG, you would have ultra weak DG, you would have different combinations. And each of them you would have to go through the stability and error estimates, and also you would have to make sure that you study this not just for fun. Your scheme should be better than the other schemes, either in terms of simplicity or in terms of some properties and so on, at least in a subclass of problems, right? Because if you are inferior in all cases to another scheme, then why study this, right? It has to have something, some selling point, some advantage in some cases. So these are all details, so I don't want to talk about them. So I basically would want to conclude here. What I want to say is that the DG methods are very flexible to geometry, boundary condition, and HP adaptivity, parallel efficiency, and so on. up to now, stable and accurate DG methods can be designed for a very wide class, very wide spectrum of PDEs, including conservation laws, convection-dominated, convection diffusion equations, dispersive equations, and so on. But there are also many issues left. What I want to say is the following, right? So usually, if you find a PDE, and then you first ask yourself, is this something that DG could have some advantage, like this recent work with postdoc here with Professor Yao, right? The postdoc Chen Yuewen. All this PDE from relativity, but of course in the simple case, in the 1D case, but still looks very messy. But that equation is a hyperbolic type, and it does have some feature that makes DG suitable choice there. For example, it could have some lack of regularity, and could have some properties, upwind, and so on. So make DG a good choice. But then when you really dig into it, you follow, it's basically, it's one word saying that what did the PDE people do, right? The PDE people proved this kind of stability and this kind of solution regularity. And you look at this 7 times and say, can I do some kind of DG which will mimic this procedure and you can get the same stability and same error estimates, right? So often you can do that after a few months. But I would not say that it's always doable, but often it may not be that straightforward. Let me put it this way. So if you say, this doesn't look the same as before because of this, of course it doesn't. Always every problem has some new feature. But yeah, usually you can get around and you can design a good method. So that would be very nice. And then you can talk about the details, let's say efficiency, right? Time stepping, or solving a large system, multi-grade, precondition, error estimates, like what I was murmuring here. So you have flexibility. You can take polynomial degree 6 here, 7 here, 3 here, 3 here. You have a choice to either cut this further in edge refinement or increase this 3 to 5. So which one should I use, right? So then if you have some mathematics to guide you to tell you the error is expected to decrease further, decrease more. If I increase the polynomial degree here, then just refining with the same computational cost, I would get more. Then of course I will follow that. So then that involves some mathematics on getting these error estimates, posterior error estimates, which would allow you to do that. Yeah, I think that's it. So I'm done, and thank you for your attention.
Okay, it's time for questions. Any questions?
Simple question.
Yeah.
Can your method use in stochastic equations, stochastic differential equations?
Yes. Yeah. We did some work in this in 2 different directions. One of them is called polynomial chaos type thing, that you make expansion, spectral expansion, and then you write your solution as a spectral sum of certain polynomials of random distributions, and then the coefficients would be deterministic, and then you derive. So this is one thing. Then, of course, in following that route, it will be the usual DG because you're solving deterministic PDEs. The other, of course, is that you put the random thing already in, just solve with, say, right-hand side noise and so on. And that you could use DG. You have some good estimates also there. There are pros and cons in these 2 different approaches. Well, we can handle data function, for example, that we would. So if it is more complicated, You mean even stronger singularity than delta. Oh, yeah. I think in principle.
Well, in principle, it could be fractal and all complicated. So
Yeah. So yes, it's a good question. So for example, if it's not piecewise smooth, I'm in trouble. Yeah, because the thing is that I'm using polynomials, right? So if it's not at least in some part of the domain, I have smooth things that is well approximated by polynomials. If everywhere I have trouble, then this will be a problem.
Suppose I would like to create a black hole solution which has a fractal dimension.
Yeah.
Which I hope could be achieved.
Yeah.
This would not be possible.
This would be very difficult to simulate, unless, of course, you build this into VH. You build it into the finite element space. Because this one advantage of DG that I did not mention is that this space just has to be finite dimensional and doesn't matter what is in it. Stability would be automatic. And then you can put the ansatz of a finite dimensional approximation to your solution, which is very chaotic, into the space. You guess the possible type of the solution, and then you make linear combinations of them, you solve for the coefficient. Yeah.
Okay, any other questions?
For talk. So when solving the problem with highly oscillator problem, do we also need that the mesh size is very small enough?
Yeah, if it's a high dimension, then
highly oscillatory. Highly oscillatory.
Oh, highly oscillatory.
Yeah.
Okay, then maybe the answer is similar to the answer to Professor Yao's question. You build this into your finite element space.
I see. Multiscale.
Yeah. If you have some guess of what kind of
just like the multiscale finite element.
Exactly. Yeah.
And another question is currently, do we have any literature about the posterior estimate for the DG method?
Yes, a lot of such things. Yeah, but mostly for elliptic and parabolic things.
I see.
Hyperbolic is a little bit more difficult, but it should be done. Yeah, because otherwise all this advantage cannot be utilized.
Okay.
Yeah.
So my last question is that is there what's the superiority of the DG method when it is applied to solve the differential equations without discontinuity or singularity or oscillation?
Yeah, not much. Yeah, so what I should mention is that DG would work for many equations, but is it of advantage in comparison with other methods? It may not be the case, right? So you have to first ask yourself whether this is something that DG will show an advantage before studying. Yeah.
Okay, I think it's the time to close the lecture. Let's thank the speaker again for the next talk.
Thank you.
If you have any other questions, please feel free to contact Professor Shu offline. Okay.